Welcome friends to the online course on risk and reliability of offshore structures. We are looking into lectures on module 2. Module 2 is focusing on reliability theory and structural reliability. In this lecture, which is a lecture 20 in module 2, we are going to talk about structural systems, that is reliability analysis of structural systems. In the last lecture we discussed that if I know the reliability index of an element, I can always find the reliability index of the entire system. We know that the reliability index of the entire system is dependent on reliability index of an element, which in turn depends on the mean and standard deviation of each element. Therefore, for the ith element, limit state function can be given by where Q I is a load effect in the ith member, of the system. Of course, without saying, for the given conditions, reliability study cannot be applied on infinite domain. Given conditions and given state and given period, given combination, you can do reliability analysis. All these are to be prescribed before we do a reliability analysis. Therefore, under given conditions, one can write this. If the strength of the ith member is normally distributed, whose mean is mu e and standard deviation is sigma e, then reliability index of the element is simply given by, or let us say reliability index this equation here. equation number. So, reliability index for the element is given by beta E, which is mu E minus q I by sigma E of the ith element, okay, for the, let us say, ith element. Now, q I, which is going to be the load effect which is required for the reliability analysis, is simply given by the mean of the element minus reliability index of standard deviation of the element. Now, since the mean, reliability index and standard deviation are same for all elements, one can expect that q I, there is a load effect, will also be same for all elements. Hence, the total load effect can be simply said as n number of elements of q I. On the other hand, q total can also be said as n u E minus n beta E sigma E, because q I is given by this equation from 4 and let us 5 here. 5. Now, the limit state function for the entire system is given by because earlier it was for the element, now it is for the entire system, and the reliability index for the entire system is given by now reliability index for a parallel system which contains with equally correlated ductile elements is given by where rho is the correlation coefficient. Calls equation number 8, which can be further simplified as which can be further said as which can be simply with element of that's it. Okay. Equation number this is square root here as well. So, now let us talk about a system with unequal correlated elements. In real structure, system has n number of elements which are generally unequally correlated. So, following assumptions are need to be made. In such analysis, 1, strength of all elements, are normally distributed with identical distribution parameter sigma e and mu e. Secondly, applied loads are deterministic and time invariant. Thirdly, all elements are designed to have the same reliability index. Beta e. Let us talk about parallel system with ductile elements. Now, let us consider a parallel system with n perfectly ductile elements. The strength of the ith element where I actually the number count of the elements be Ri, and let the strength of the entire system be simply R. Now, since we are talking about elements with unequal correlation, we need to also establish a correlation matrix. So, the correlation between the elements parallel is given by the row matrix, which is going to be unity row n 1 n, row 2 1, unity row 2 n, row n 1 1, row n 2, let us say row n 2, etc. So, that is going to be the matrix which we call as equation number 10. Now, the reliability index for the system is given by mu r minus q total by sigma. Okay, 11. Now, mu r is of course n mu e, variance is summation of rho I j sigma r I sigma r j, which can be said as which can be further said as therefore, we can say sigma e square n plus summation to n I naught equals j I rho I, equation number 40. Now, let us imply that all elements are subject to the same load. In that case, system reliability will be given by rho I j, equation 15. Which can be n sigma e by root of sigma e square n which can be simply beta e equation number 16, which further simplifies to beta e root of n by 1 plus 1 by n of summation of I naught equals j I n rho I j. Now, as we understand that all members are unequally correlated, we can use an average correlation coefficient. Which I call as rho bar. So, rho bar, which is the average correlation coefficient of all the members, is given by 1 by n of n minus 1 double summation I 1 to n I not equal to j n rho I, equation number 70. Combining the above equations, one can write the system reliability as, let us say, combining the above equations, system reliability is given by element reliability by 1 plus n minus 1 rho bar, equation number 8. So, we discussed about the reliability estimate of a structural system comprising ductile members in parallel with unequal correlation coefficient. Now, let us talk about the reliability bounds for structural systems. In system reliability, it is often convenient to work with Boolean variables. Okay. So, it is rather convenient to use Boolean variables for system reliability. You may ask me a question, why it is so? System reliability, which is consisting of elements maybe in series or in parallel, is amounting to failure of an element amounting to failure of a system, or failure of all elements amounting then to failure of the system. So, it is talking about only either success or failure, either performing or non performing. So, it is always easy and convenient to use a Boolean variable for system reliability. Okay. Let us say for example, consider n elements. We also assume that each element can exist only if one of the two states are existing. Namely, failure or non failure, only two states. Now, to describe these two states in Boolean variable, let us try to use certain variables. Describe these two states, let us use Boolean variables Si and Fi. Which are defined as follows. Si will be actually equal to 1 if the element is a non-zero failure state, it is 0 if the element is in failure state. Fi, which is also a Boolean variable, is 1 minus Si, which again says 0 if the element is a non failure state, because it is 1 minus Si. For Si 1, Fi becomes 0 for a non failure state, and obviously it is 1 if the element is in failure state. Now, based on these states for elements, one can define the state of the system. State of the system using Boolean variables. Let us say using Boolean variables S bar and F bar. S bar is a set of S1, S2, Sn, and F bar is a set of F1, F2, Fn. Now, the system function is defined as SS S bar or Fs F bar. This will now indicate the state of the entire system. Okay? We can write it here, which will indicate the state of the entire system. Now, the function is defined as SS S bar is 1 if the element is in non-failure state, it is 0 if the element is in failure state. Similarly, Fs F bar is 1 minus Ss S bar, which is now 0 if the element is in non-failure state, because for non-failure state Ss S bar is 1. Since Fs F bar is 1 minus this, so for a non-failure state this becomes 0, okay, and of course it becomes 1 if the element is in failure state. Is it okay? Now, for the system in series, failure of one element means the system failure. Now, for a structural system in series, failure of one element means system failure. For the system in parallel, failure of one element or failure of all elements means system failure. Now, hence the system function can be expressed as Ss S bar is S1 S2 Sn, which is nothing but pi I equals 1 to n Si. If the ith element is in a failure state, I will call this equation number 13. If ith element is in failure state, then we know that Si is 0, and hence the product as shown in equation 13 will also be 0. If none of the elements have failed, then all the Si values are equal to 1. That is the non-failure state. Therefore, the product will also be equal to 1, which indicates non-failure state. Now, for a parallel system, this is for the system in series. For a parallel system with perfectly ductile elements, if at least one element is in non-failure state, then the system is in non-failure state. Therefore, the corresponding system function is given by SSS bar is 1 minus pi I equals 1 to n of 1 minus Si, equation 14. Therefore, looking at the equation 14, one can say that if one of the elements in non-failure state, if one of the elements is in non-failure state, then 1 minus Si will be 0, which is true for that element. Product will be 0 and the resulting function will be 1, which implies that the system is in a non-failure state. Now, using the Boolean variables, one can also compute the expected values and probabilities. Let us say consider the ith element of the system. If the state of the element is random, Si then becomes a discrete random variable. Therefore, there are only two possible ways or values. So, it can assume only two possible values, 0 and 1, and the probability associated with each value can be calculated, which we will discuss in the next lecture. So, friends, in this lecture we are able to understand how to compute the system reliability for known element reliability if the elements are in series and parallel, if the elements have equal correlation coefficient, if the elements have unequal correlation coefficient, where we replace the correlation coefficient by a average value rho bar from a matrix what we have computed and shown in the lecture. So, interestingly, for system reliability, it is more convenient to express the reliability of the elements in Boolean variable. Therefore, system reliability can associate only with two problems or possible values 0 and 1. Then in that case, the probability associated with each of this value can be interestingly studied and can converge to system reliability very easily with a better understanding. Thank you very much.